Hello, welcome back. Good to see you here again. Today we're talking about the fundamental theorem of calculus and definite integrals. Our learning objective will be to evaluate definite integrals analytically using the fundamental theorem of calculus. Just a note, I'm going to go through the evaluating of functions really quickly. I think you can plug in numbers and simplify. So please pause the video if you need time to write the numbers down. We talked about the fundamental theorem of calculus in the last lesson, and basically what we learned was that anti-differentiation and differentiation are inverses of one another. So if you take the derivative of an antiderivative of a function, you basically just get the function back. It's just that f of t becomes f of x because you've evaluated it at x. Now we want to turn our attention to the fundamental theorem of calculus part 2, which will give us a tool for computing definite integrals in a quick and efficient manner. Given that f represents the rate at which the function big F is changing, that is, little f is the derivative of big F, we know that this notation here represents the total net change in f on the interval from a to b. So the fundamental theorem of calculus is this. If little f is continuous on ab and big F is an antiderivative on the interval, then what we know is the area under the curve of f of x is the antiderivative evaluated at b minus the antiderivative evaluated at a. Sometimes you might see this guy in the middle here, big F of x evaluated from a to b. All right, so let's give this a shot. We have the area under the curve from 1 to 2 of x squared minus 3 dx. So this is what this looks like graphically. X squared minus 3 is this parabola, and the area under the curve from 1 to 2 is these, little green spots that I've colored in here. That's what we're trying to find. So we'll take the antiderivative of x squared minus 3. You get 1/3 x to the third minus 3x. And now we will evaluate that from 1 to 2. So this green function here is now 1/3 x to the third minus 3x, just so you can see the antiderivative, and we want to know the difference in the y values from 1 to 2. In other words, f of 2 minus f of 1. So we'll plug in 2 to the function. This is f of 2, and subtract f of 1. Simplify it, and we get negative 2/3. Let's look at our graph again. What is the difference in the y values? So negative 3.33 minus negative 2.66 is, negative 2/3. Let's give this one a shot. First thing we're going to do is rewrite it a little bit. So this 3 is a constant. I can pull that forward, and then the square root of x I'll write as a fractional exponent. Now I can take the antiderivative of x to the 1/2, keeping the 3 on the outside. Okay, the antiderivative of x to the 1/2 is 2/3 x to the 3/2, and now we will evaluate that from 1 to 4. So that'll be f of 4 minus f of 1. Before we just dive in though, let's clean this antiderivative up a little bit because that'll make it a little bit easier to see and to deal with. So this is f of 4 minus f of 1, okay? And this 2 I just kept on the outside. That's optional, you don't have to do that. Simplify. 14. Next one. First thing we're going to do is rewrite this thing because we can split this into 2 different fractions with fractional exponents. And that just makes it easier to see. It makes it easier to take the antiderivative. So then we'll do that. We'll take the antiderivative of each of those pieces. 2/3 x to the 3/2 minus 8x to the 1/2, and evaluate that from 1 to 4. Plug in 4, plug in 1. F of 4 minus f of 1. Whoop, that should be a capital F. Simplify, and you get negative 10/3. We'll do a trig function. Antiderivative of sine of x is negative cosine of x. And the antiderivative of 1 is x. Evaluate that from 0 to pi. So this is f of pi minus f of 0. Simplify, we get 2 plus pi. What would this look like in real life? We're going to translate these couple scenarios here into English. If f of t represents the rate at which your 401k changes in value over the month of January, then what does this definite integral represent? What's the area under the curve from 1 to 31 of the rate? That would be the total change in the value of your 401k in dollars for the month of January. Next one, if R of t represents the rate at which your pizza changes temperature in a 407-degree Fahrenheit oven, 5 minutes after the pizza has been placed in the oven to cook, then what does the following definite integral represent? So the area under the curve from 5 to 20 of our rate, that's the total change in the temperature of the pizza from 5 minutes to 20 minutes. You're at a football game, and A of t represents the rate at which fans get in line to buy tickets, and P of t represents the rate at which they buy their tickets and leave the line. So what would the area under the curve from 1 to 5 of A of t be? That would be the number of fans arriving from 1 to 5 minutes, or the number of fans that got in line from 1 to 5 minutes. What about 1 to 5 of P of t? That would be the number of tickets purchased from 1 to 5 minutes, or the number of fans who left the line from 1 to 5 minutes. Okay, what's A of t minus P of t? There's no integral sign, and those are both rates. So that would be the rate at which the line is growing or shrinking, depending on which one's bigger, right? A of t or P of t. Now, if we integrate that from 1 to 5, that's the change in the number of fans in line at 5 minutes. So far, we've been looking at examples in which the derivative of a function's antiderivative gets you back to the original function. In other words, if you take the derivative of the antiderivative of a function, well, you just get the function back again. This x just replaced the t. However, that isn't always the case. What if the upper bound here isn't just x, but a function of x? Here's Jim, and remember, Jim means that you need to just put your pencil down, stop taking notes, but really pay attention and watch so you can just get the overview of what's happening. Find the antiderivative, f of x, then take its derivative and see what happens, okay? So we're going to take the antiderivative of 3t squared from 2 to x to the 4th, okay? So that means we got to add 1 and divide by it. So we get t cubed evaluated from 2 to x to the 4th. Now we do f of x to the 4th minus f of 2. Clean that up a bit, and we have x to the 12th minus 8. That's the antiderivative. Now let's take the antiderivative and take the derivative of it. So the derivative of x to the 12th minus 8 would be 12x to the 11th. That 8 just boop, disappears. Now that doesn't look anything like my original function, does it? But I'm going to do some rearranging here. So that 12x to the 11th, I'm going to separate that into 3x to the 8th minus 4x to the 3rd. Then I'm going to rewrite it to be 3x to the 4th squared times 4x to the 3rd. Okay, now this part should look familiar because that x to the 4th, well, that was our upper bound. And it just got stuck into where the t was in the rate function. But where did this 4x to the 3rd come from? That is the problem. So a more general form for the fundamental theorem of calculus looks like this. If you're taking the derivative of an antiderivative, but you're going from a constant to a function, then the function gets plugged in to where t is. Then you have to take the derivative of that function. What if both the bounds are functions? So if you have h of x on the bottom and g of x on the top, same thing. You have the fundamental theorem of calculus here, f of a minus f of b. But each time you are plugging in a function, you have to take the derivative of it. So f of g of x times g prime of x minus f of h of x times h prime of x. So let's see how we would put that together. We're going to find the derivative of f of x. So we're finding the derivative of an antiderivative of e to the t squared. Because x squared is a function, we need to keep in mind this more general form of the fundamental theorem of calculus. So g of x is just going to get plugged in to the t part. So x squared just gets plugged in to the t part here. So we have e to the x squared squared. Then we multiply that times the derivative of x squared, which is 2x. And then you can clean it up. Okay, a couple things I want you to be watching for. If it says evaluate the integral, -3 to 6, and you're like, oh, I totally know how to do this. I can integrate each of those polynomial pieces and evaluate from -3 to 6. However, notice, between -3 and 6, this 2 over x term is a problem because x can't be 0, but 0 is between -3 and 6. See this graph here? That vertical asymptote of 0 is a problem, and this integral cannot be evaluated like it is here. What happens if we get absolute value? Let's graph this thing so we can see what's going on. We want the area under the curve from 0 to 4, so we've got a triangle there and a triangle there. Now, this part here, that's not differentiable. So we're going to have to split this thing. What is that point there? It hits the x-axis at 2.5. So we're going to split this integral, okay? We'll go 0 to 2.5 and then 2.5 to 4. And then you're just doing the same thing as before. You're just keeping the absolute values throughout so that when you evaluate it, everything should be coming positive. So if I plug in, this is f of 2.5 minus f of 0, and then f of 4 minus f of 2.5. We add those together. Okay, so watch this guy right here. So -6.25 minus 0, see that absolute value is still on it? So that becomes a positive 6.25. And then you can keep simplifying. The final area is 8.5. Ooh, a piecewise function. That's fun. It says, consider the piecewise function below. Set up but do not evaluate the following integrals. So we're just going to set them up. We're not going to do all the math. So we're going from 3 to 8 f of x dx. Well, if you look at the piecewise function, we've got x is greater than 1 and x is less than or equal to 1. So 3 to 8 is going to be using the bottom function for x is greater than 1. So that's what we're doing, 3 to 8 of 5 dx. What about negative 2 to 4? Okay, we're going to have to break that up at 1 because from negative 2 to 1, we have to use the top function. And then from 1 to 4, we have to use the bottom function. Let's talk about how to integrate with your calculator. Unleaded gasoline is being pumped into an empty underground storage tank for the opening of a new convenience store at the rate of 600 root T gallons per hour. How many gallons of gasoline can the supply truck deliver if it pumps for 2 hours? So again, we have a rate of 600 square root T. If I want the total number of gallons pumped during that 2 hours, I need to integrate that from 0 hours to 2 hours. So grab your calculator, go into the equation editor, the y equals, and plug in your rate. Then get out of that and hit Math 9. So see, it says function integration. And then let the calculator do the heavy lifting for you. You just have to plug in your bounds and bring in your y1, hit enter, and there we go. 1,131.37 gallons. Oh, I like this problem. If f is an antiderivative of cosine x squared over e to the x such that f of 1 is 1/3, find f of 0. Now the key to unlocking this problem is remembering the fundamental theorem of calculus. So let me set this up for you. Our bounds are 1 to 0, okay? So the area under the curve from 0 to 1 of cosine x squared over e to the x equals f of 1 minus f of 0. This f of 0 is what I'm trying to find. Well, do I know the rest of it? Can I just solve for f of 0? I sure can. I know that f of 1 is 1/3 because it told us that in the problem. And then this guy, I can use my calculator to figure that out. So if you plug in that whole thing to your calculator, you get 0.59005 equals 1/3 minus f of 0, and then you just get to solve for f of 0 with your algebra. That's that, the fundamental theorem of calculus, part 2. Thank you so much for joining me today.